So what other shrinkage methods you think we can come up with? What is it? Each of beta is close, right? So we imposed a L2 norm on the betas, L2 constraint on the beta. You can impose any other norm constraint on the betas, right? I can impose an L4 norm, or more commonly I can impose a L1 norm, right? It's called lasso, right? So lasso is essentially right. So just the norm of the absolute value of the betas, you sum up those and you want to keep them. So you can write the same, you can write the constraint formulation where I can say sum of beta has to be less than some t, right, sum of mod beta has to be less than some t, or I could just do this kind of a formulation, right. And so to impose a constraint on each individual beta would require you to know something about the variables themselves beforehand, right. Otherwise if you constrain a very important variable to have a small coefficient, then it becomes a problem. So you need to know something about the variables, and you can say, okay, I know that these variables are very important, make sure that the other variables do not amount to more than 0.5 times the coefficient of these variables or something like that. You can think of all kinds of complex constraints once you have knowledge about the system, but typically you do not, right. In such cases you will have to have some kind of uniform constraints like this, and so this is a very popular constraint. It actually makes life harder for us, right. So it does not have such a nice closed form solution anymore. Why? I mean, this is no longer differentiable, right. So I can't write your nice closed form solution like this. In fact, I have to work very hard to solve this. Okay, there are packages. I mean, you don't have to work very hard. I mean, I'm just telling you typically. So so you can just run it on R or Vika or something. You can always run lasso on it. It will give you the nice fit. So what's the nice thing about lasso? I'll try to give you an intuition about it. So think of it this way. So suppose I have a non-important coefficient, okay. So if I can reduce it from say 1000 to 0.3, okay. Well, let's not even look at it that way. So I can reduce some coefficient from say 1000 to 999, okay, right, and there is another coefficient which I can reduce from, let us say, so there are many variables in my fit. There is one variable whose coefficient I can reduce from 1000 to 999. There is another variable whose coefficient is 1, I can reduce it from 1 to 0, okay, and both of them cause the same change in my squared error, okay, both of them contribute equally to the squared error, and making this change will make the same change to the squared error. So which one would ridge regression prefer to reduce? 1000 to 999, because that causes a much larger reduction in the squared penalty, right. Which one would lasso prefer to reduce? Does not matter, either one, but then I can make this thing slightly more contrived. right. Now we go, which one would lasso prefer, right. So even though this is a absolute values, this is a larger reduction, Ridge would still prefer 1000 to 999, right, because the fall is 1.1 squared to 0 squared versus 1000 squared to 999 squared, right, still that is a larger reduction in error, right. So what is the take home message here? Lasso is more likely to drive coefficients to 0 than Ridge. So Ridge would happily leave the coefficient at 1.1, right, or even more dramatically it will happily leave coefficients at 0.3, 0.2, 0.8. So it will leave it at small values, it will not drive it all the way to 0, okay. While lasso, given an opportunity, right, will drive the coefficients to 0. I mean it will not do it 0, drive it to 0 at the cost of minimizing the error, right, it will still try to minimize the error, right, but given a chance it will more likely to drive coefficients to 0, okay. So in sometimes lasso is also called sparse regression, right, because this L1 norm constraint is also called a sparsity constraint, because it makes your beta vector more, will have to have more zeros, right. So if you know what a sparse matrix is, right. So you have a matrix with a lot of 0 entries in it and only few non-zero entries, you call the matrix a sparse matrix, right. So people worked with sparse matrices, right, some of you have worked with sparse matrices. So you really do not want to have an array representing a sparse matrix because most of the entries are 0. So typically what you do in a sparse matrix representation is you store the index of the non-zero entry and the non-zero entry, okay, that actually takes a lot less memory than actually having a large m by n array with lots of zeros. So that's why it is called sparse things. So here the L1 regression has a tendency to make the beta sparse, okay, it will have a lot of zeros. So it is sometimes called a sparsity constraint.
We have coefficient less than 1 and 1 is 0. In that case that will be better than this one.
Coefficients less than 1, all the coefficients are less than 1 you mean?
As in 1.1 and 0 you take,
yeah.
In the other case as 0.1 and 0 something like that.
Yeah.
In that case when you square it will become lesser.
Yeah.
So the Ridge will become better than that.
No, see if I take 0.1 and I square it, okay, and the difference between that squared and 0 squared is lesser than 0.1 and 0.
So
No. So, but the drop in the value, yeah, will be bigger in the lasso than in Ridge. Okay, now it depends on what other competing elements that you have.
So it depends on the coefficient also.
Well,
you
yes.
can't say lasso is better than Ridge in all cases.
No, lasso is typically drives the coefficients to 0 while Ridge does not. I was giving you an intuition as to why that is the case, right. It is not mathematically a sound argument, but you can give a mathematically sound argument also that lasso is more likely to find sparse fits than Ridge regression, okay. So I am being very careful. I am being careful. So I mean I can also think of a geometric intuition for it. So if you think about the right, the lasso constraints will be something like this, right, and you think about Ridge constraints, that is supposed to be a circle, okay. So the Ridge constraint will be something like this, right. So here if you remember the sum has to be a constant, right. So the sum has to be a constant and the sum of squares has to be a constant. So one will be a circle, the other one will be a thing. So when you are looking at the error surface corresponding to this, right. So essentially you will have to find solutions that lie on this or lie within this for Ridge, I mean for lasso, and lie within this for Ridge, okay. And it turns out that you are more likely to hit a corner of, you can show that more formally, that you are more likely to hit a corner of the in the lasso case, and in the Ridge case you are likely to hit, I mean, so the probability of hitting something, because this is the whole thing is convex, the probability of hitting that side is higher, right. So we can, this is just the very rough intuition, I do not want to get into showing things formally, but you can show that the probability that lasso will give you these kinds of corners in the fit. A corner obviously you can see that has one of the coefficients as 0, right. So that you will get a corner as a fit is much higher than you will get one of these axis points in the ridge. Okay. So, okay. In fact, you can think of having higher order penalties also. Okay, you can, like I said, you can think of an L4 norm penalty, right, and you can even think of. So far we looked at two methods for variance reduction. So one was subset selection, okay. The other one was shrinkage based methods, okay. Now there is another third class of methods which people use for getting better fits with possibly fewer variables or fewer parameters. This is based on derived input directions, right. So we talked about reducing the number of variables so far, right, but in both of the I mean at least in the subset selection part we retained some of the variables and then we ignored some of the other variables, right. Likewise, whether we are doing implicit subset selection by doing lasso or ridge regression, we are reducing the coefficients of some variables and retaining some other variables, right. But at all points we were operating with the original set of basis vectors that were given to you, right. So what were the basis vectors we are talking about here? What are the basis vectors you are talking about here? The columns of the X matrix, right. The columns of the X matrix are the basis vectors. So we are working with the original basis vectors, we are working with the same columns that were given to us, right. We, in one case we picked some columns and threw out some of the other columns, in the other case we tried to continuously adjust the weights of the columns so that some of them were given more weight and some were given less weight. So when we talk about derived input directions, now I am not going to stick with the original columns, okay. I am going to find a new set of columns, right. I am going to find a new set of features, new set of directions, right, which I will then use for doing my regression, okay. So we actually talked a little bit about it in the when we looked at the orthogonalization, right. I told you when you do orthogonalization essentially what you are doing is you are finding an orthogonal basis for the input space and then you are trying to find the coefficients there. So likewise what we will do here is right. So we will reduce the dimensions, okay, as I put it in quotes, I will explain why, and then we will also orthogonalize the dimensions, okay. So what is the advantage of orthogonalizing the dimension? We could do univariate regression on each dimension separately, okay, and then that will give us the coefficients, okay. So we do not have to actually do a multivariate regression, okay. We can do univariate regression on each dimension because once I orthogonalize the directions they do not interfere with one another, right. So I can do univariate regression. So typically when I try to do this derived input directions I try to orthogonalize the directions, okay, and I also try to find a reduced set of dimensions that will give me the original fit or as close to the original fit as possible.